Okay, so it is our great pleasure this week to have Professor Mikhail Belkin, who as a UCSD faculty member, I also feel lucky that we have at UCSD now. He will be giving a talk on the theory of optimization, but before, and transition to linearity and deep learning. But before I give the floor to him, a few words. Misha has been doing very influential work in a number of areas related to data science and machine learning for a number of years. He's perhaps one of the works that come to mind is his work on Laplacian eigenmaps, but he's also done work on various other things ranging from graph regularization to manifold regularization and other topics in learning theory. And most recently, he's been interested in questions about machine learning and in particular deep learning related to generalization and optimization. He's had some influential work in those areas. I'm very excited to hear what he has to say today. So I will turn it to him.
Thank you very much, Ryan, for your kind introduction, and thank you for inviting me to give a talk. I would like to talk about optimization and transition to linearity in deep learning, which is some fairly new things. And first, I should say that most of the work I'll talk about today is joint work with my students, Chao Liu and Li Bizhu, and who did a lot of work on this, and I learned a lot from them. So now, and by the way, I should say, please feel free to ask questions, and I'll try to also look at the chat, but certainly feel free to interrupt me and ask questions. So a lot of inspiration for for theoretical work recently came from the fact that we have this amazing object, deep neural networks, which seem to work really well in practice. And yet we had somehow very little understanding of what they do, how they work. They looked like very complex black boxes. And in fact, it seemed that a lot of what they did was somehow almost contrary to our expectation, and like from theory, what they should be doing. So, these are objects like this. And clearly, we cannot understand like every little detail of an object like this. We have to understand some general principles of how they operate. And today I will talk about two things related primarily to optimization, but also, well, this transition to linearity, which is related to optimization, not exactly optimization. Let me start with a sort of a setup. In machine learning, we deal with models. And how does it work? Well, we're given data xi, yi, and we are looking for a function f which fits the data. That's basically what empirical risk minimization is. And if it's a parametric family of functions, in this case, f of w, we are trying to minimize something called the empirical risk, which is just fit to the data. In this case, L can be, for example, the square loss, and that's mostly what I'll discuss in this talk, where L of fwxi, yi is equal to just difference fwxi minus yi squared. And specifically, this is optimized by methods such as stochastic gradient descent or gradient descent, relatively simple first order methods, and their variations with momentum and so on. And the first question is, well, let me start with this quote, which is, sort of sets it up, I think, very nicely. And this is from Bruce Lund's tutorial at the Simons Institute in 2017. And he said, well, the best way to solve the problem from the problem of machine learning, from the practical standpoint, you build a very big system. And basically, you want to make sure you hit zero training error. So your optimization algorithm for this problem has to output something with zero loss, or close to zero loss. Now, this is not the end of training, and you need more to get state-of-the-art results in machine learning, and because we don't actually care about the training performance, we care about generalization, which is performance in the test. But it turns out that even if you just do this, you already get pretty good performance for your test data. And perhaps the first question is to ask, why is it that when you build a very big system, you can hit training error? Why does it even make sense? And sort of classically, if you think about it, it almost seems like it doesn't make sense. And I'll discuss this in a minute. But first, let me point out something which I think is kind of amusing, but also a little bit illuminating, is to just what is the notion of this large model? And if you look at the technology, you realize that sort of with time, these models have become significantly bigger. To sort of validate this previous point, you essentially want to be as big model as possible. So this is the diagram from Kanziani et al. 2017. They represent each neural network. So each circle here is a neural net. And the size of the circle, the area actually of the circle, is proportional to the number of parameters. So the small circles here are about 5 to 10 million parameters, and the big one are about 150 million parameters. And the one actually I showed you before in the second slide, it's actually one of the smaller ones that has about 6 million parameters. Now, well, this was from 2017, of course. This year is 4 years later. So now, in 2020, actually, the GPT-3 was the largest model, and it has 175 billion parameters. So that's what it looks like. This is to scale. And of course, things move quickly here, right? So now it's even 2021. So this is not the largest model anymore. The largest model is something called switch transformers, which has 1.6 trillion parameters. So this large numbers of parameters is a very real thing. Like we literally want to build as big, well, the industry, I don't know, the practitioners want to build as big a system as possible, like technologically. So, okay, now this is the setup. What am I going to talk about today is the following questions. The first one is why highly over-parameterized systems are non-convex, and this is generally true, but yet in a sense easy to optimize. And this actually, the explanation is given by something called Polyak-Lojasiewicz condition. And the second one, so this is based on 2 papers actually, is something called transition to linearity, which was observed a couple of years ago. And I would like to discuss why it turns out remarkably that some linear networks, not all, but some wide linear networks actually are linear functions of the parameters, which is, I think, an absolutely remarkable thing and really, really quite unexpected. So to me, that was a big revelation when they discovered this. And I'll discuss somehow maybe a simpler way to think about it, and also the limitations of this. So first, I would like to take the perspective of interpolation. And what does it mean? So what's interpolation, right? Interpolation is when we fit some data points exactly. And it turns out that, and I will not discuss this today, but it's a pretty interesting thing, because usually we believe that fitting noise, statistically we think that fitting noisy data exactly is a bad thing. And now we're starting to understand that it's not necessarily a bad thing. In fact, fitting noisy data exactly may be quite okay. But from the optimization point of view, we don't have to worry about that, because we can just think, okay, I just have a problem of fitting the data, I'm just going to solve that. And now the nice thing is that once you take this perspective that you just want to fit the data, your optimization problem is equivalent to simply solving a system of nonlinear equations. I just want f of w of xi equals yi. So the number of, it's a system of equations with a number of equations equal to the number of data points. And the dimension of the W space, the number of variables, equal to the number of parameters of the system. So I can kind of combine it, just write f of W equals y, where f is a function from Rm to Rn. Now, fundamental question here is, when can a system of nonlinear equations be solved? And well, if you kind of think about it from this point of view, it seems a little bit bizarre to ask this question, right? Because, you know, like there are many areas of mathematics which very subtle, which deal with this question, like algebraic geometry is essentially answering this type of question. So how can I ask a question like that? Well, it turns out that there are some, when the systems are over-parameterized, we will see, that, that there are some kind of generic answers to this. And of course, a kind of obvious observation is that this is equivalent solving system, f of w equals y, assuming there is a solution, of course, is equivalent to minimizing f of w minus y squared. Now, from a classical point of view, if we have a non-linear system, non-convex system, it's a bad thing, right? Because there are usually many local minima, and in general, there is no global optimization technique, which allows you to choose a global minimum, this one, out of this local minima. So that seems kind of like a hopeless problem in general, and certainly gradient descent type techniques are not going to work here, because, you know, if you start your gradient descent here, you will very nicely converge to this local minimum, but you will never find this one on the left. However, we know that we can train neural networks and they fit data quite nicely. So what's going on? And we know that they're not convex, of course. That's not hard to see. So what's going on? And the answer is that, in a sense, this is a wrong picture. This is a wrong mental picture. This lives in the under-parameterized world, when the number of parameters of a system is smaller than the number of variables. Once we live in the over-parameterized world, the picture is different. So on the left, you have this kind of under-parameterized world. You have local minima. They're isolated. And I actually noted that around each minimum, this function is actually convex in a small neighborhood. When you have over-parameterized system, a typical landscape looks like this kind of S-type curve on the right. There is a valley of global minima. And as we'll see in a second, it's not convex at all, like not even locally. So why is this landscape? So there are a couple of questions. First, why do neural networks, or generally, more generally, over-parameterized systems have this kind of landscape? Oh yeah, and I should also point out that if you use gradient descent on the left, it's of course the same thing, right? You kind of converge to the nearest global minimum, local minimum, right? That's what gradient descent does. You kind of roll a ball downhill. If you do it on the right, your ball rolls down to the valley, so you find a global minimum. So somehow the landscape on the right is conducive to optimization, to finding global minima. The landscape on the left is not. So let me now point out why the landscape on the right is not locally convex. So suppose I take a small neighborhood of a point here, and I have this kind of ellipse or circle. And let's look at the set of minima within the circle, which is what I have on the right. Now, if my function is locally convex, even in this little ball, then we know that the set of minimizers of a convex function is also a convex set. So if L of W, if this loss function is locally convex, then that better be a convex set, and the only convex curve is a straight line. So unless there is no curvature somehow to this curve, this cannot be convex. And of course, generically, a manifold of global minima is not going to be an affine subspace. So we see that this is a kind of generic fact. So the first maybe kind of conclusion based on just this simple pictures is that theory of optimization for over-parameterized systems cannot be based on convexity. And that may be, it may be a simple thing, but I think that was kind of a confusing factor for years because, you know, most classical analyses are based on convexity, and it's kind of hard to think of optimizing non-convex problems in general. So, of course, this is not a completely satisfactory question. It's not a satisfactory statement because, well, if it cannot be based on convexity, what should it be based on? And the alternative proposal is instead that over-parameterized system satisfies something called Polyak-Lojasiewicz condition. And I put a star here because it's a minor modification of that condition. I'll explain that later. And so here is a plan. So first, I'll discuss the Polyak-Lojasiewicz condition. Then I will talk about why Polyak-Lojasiewicz condition is sufficient both for existence of a solution and guarantees an efficient optimization. And I also will show how this condition can be analytically verified. It's controlled by the smallest eigenvalue of something called the tangent kernel, which is essentially just the derivative of the function. Okay, so now Polyak-Lojasiewicz condition is simply the following. We say that L satisfies PL if gradient of L squared is bigger than some mu positive number, L of W minus L of W star, when this is the minimizer of L. So notice a couple of things. Well, first, this is clearly a simple first order condition. Second, it guarantees convergence of gradient descent. And that's what Polyak proved originally in '63. And third, which is a really nice property of it, this condition is kind of invariant under nice transformation. And what do I mean by this? Well, this part, why is it not working? This part is simply the values. So suppose I transform my space, then essentially I just need to control the gradient. So if my transformation has a nice Jacobian, the gradient will be controlled, and I can verify that in the transformed space this is still true. And this is actually much nicer than convexity in that sense. And let me, it's a slight tangent, but it's kind of nice to point out. Because, well, the gradient, of course, satisfies its, well, it's simply the derivative. If you have one dimension, it's just a derivative, right? It satisfies a chain rule. So if I do composition, then they just multiply. So I just need to know that both of the things are non-zero. That's essentially. Now, if I want to check convexity, well, the sort of practical way to check convexity is to look at the Hessian. The Hessian needs to be positive definite, or positive semi-definite. In one dimension, okay, this is simply second derivative. And of course, we all know that I write second derivative, I get this expression. And how do I check that the second derivative of a composition is positive? Well, the fact that the second derivative of phi itself is positive doesn't help me, because it guarantees that the first term is positive. That's phi prime prime times f prime squared. That will be positive if phi is convex. But this, I have no control over. So I cannot generally show that when you transform a convex function, you get something which is convex as well. And that's why on manifolds, for example, you cannot define this invariantly. You can define it maybe in a geodesic system of coordinates, but then it's a very tricky thing to check. You have to actually know some sort of form of the geodesics. PL, on the other hand, defined on things like manifolds invariantly. Okay, now going back, let's look at the PL condition again. And we realize that this condition has one issue, is that it's actually really difficult to verify. Why? Because we have to know something about L of W star. And without knowing W star, or that it even exists, maybe, you know, how can I possibly check this? So it looks like a little bit of a chicken and egg problem, right? I have to know this condition to prove that L of W star exists, but I have to know that it exists to even verify this condition. Turns out that there is a really, really simple fix to this, and you can just remove the star. That's what we call PL star. And this is wonderful because you have all properties before, plus it's easily verifiable pointwise, right? You just need to check that the gradient is bigger than the value. And it also guarantees existence of solution, and it guarantees everything as before, if it's satisfied in a ball, and big enough. So that's a PL condition. Now, of course, we need to check that this PL condition is satisfied, and for that we need some sort of analytical tool. And it turns out that we can simply use something called the tangent kernel, and actually it comes from this neural tangent kernel, specifically for neural networks, but it's simply the derivative. So what is the tangent kernel in this case? You just take the derivative, which is a matrix, right? And so it's n times m matrix, and you multiply it by the derivative transposed, and you get an n times n matrix valued function. So I'm going to skip the proof of it, but it's very easy to see that if that matrix is well conditioned, then the function is PL, and specifically this mu in the definition of PL is exactly the minimum eigenvalue of this tangent kernel function. So this gives us a very nice, the proof is actually really simple, it's just like two lines. I have it here. So this gives us a very nice analytical way of controlling PL condition. And once you have this, you can prove existence of solution, and it goes back to actually Polyak. Basically, it says that this is slightly hand wavy way to state it, but yeah, if a system of nonlinear equation is well conditioned in terms of this lambda min, then it has a solution in a ball. And what the ball is, as the radius of the ball is something like lambda min. So that's. Oops, sorry. So that's all I need to check. So I need to check that essentially I have a ball of radius 1 over lambda min, and it satisfies this condition in a ball. Now you can prove the sort of corollary of this for gradient. Well, it's not exactly corollary, but it's a related claim for gradient descent, is that if you have this kind of well-conditioned system, you can show that gradient descent converges, and in fact, the rate of convergence is controlled by this nonlinear condition number. So unlike the linear condition number for a linear system, you have to take sup of lambda max and inf of lambda min rather than just a ratio. So this maybe is the summary of what I discussed, is that it says that well-conditioned nonlinear systems behave like linear systems under gradient descent, except that the condition numbers are non-constant. And so you need some sort of uniform bound on the condition number in some ball which is large enough to ensure convergence. And in that sense, nonlinear systems, when they're over-parameterized, actually are very, very similar to linear systems, at least as far as gradient descent and existence of solutions are concerned. Now, the interesting thing that we will discuss this in a little bit more detail is that under-parameterized system cannot be well-conditioned in the sense, but over-parameterized system generically, in a certain sense, are. So this only applies to over-parameterized systems. So this is kind of this new world when the number of parameters is larger than the number of constraints. And finally, one can also prove convergence of stochastic gradient descent. And, it's essentially the same type of thing, although the ball needs to be a little larger for stochastic gradient descent to converge. And maybe I'll skip this. The kind of interesting thing is stochastic gradient descent under interpolation, when the conditions are satisfied exactly, looks very different than in the classical setting. It doesn't oscillate essentially. The variance goes to 0. But let me skip this. So now let me give you some intuition why over-parameterized tangent kernels are well-conditioned, and then I discuss how you can prove it for some classes of neural networks.
We have one question from Akram Al-Drubi. What happens when we start the ball in PL? Akram, I don't know if you want to unmute and ask your question.
Well, this is all I want to ask. So, you know, when you have this convexity alone, we kind of start far away, and we may end up in local minima. And here, if we start far away, what happened? What do we know?
Yeah, so maybe I can kind of draw a little cartoon. Let me find a white space. Okay, so here, so imagine this is my space of parameters. Okay, this is all W's, and then what happens is that in some sense, this lines are sets when my tangent kernel is singular, and there are these big regimes, big domains where you have PL. And if you start inside one of this, then you're guaranteed to converge. But if you happen to start outside of this, like here, then there is no guarantee.
Thank you.
So in some sense, I'll discuss this in a second. In some sense, it's kind of a generic condition. So you expect most points to be in one of those
things. Thank you. So
actually, I'll have it here. Let me explain it. Let me give it this very simple example, which kind of shows why we would expect something like that. So imagine my tangent kernel. So my tangent kernel is df times df transpose, right? And it's kind of a skinny matrix in the horizontal direction. So it's long and thin like this. When I multiply these two matrices, right, I get something which is n by n. And suppose n is small. Well, let's think about what it would mean for this kernel to be badly conditioned. Well, what badly conditioned? Okay, let's say I just want it to be derivative. I just want it to be singular. And suppose this matrix is, just one in this direction. It's just 1 by m. And this is going to be just 1. Then the only way in which this product can be degenerate if every entry of this thing is equal to 0. So this is a very strong condition. It's very difficult for this matrix to be degenerate if my matrix is long enough. But of course, when it's not as long, it's easier because I have fewer somehow constraints. And the same happens when I have n by m. If m is much, much bigger than n, I basically never expect this to be poorly conditioned. And in fact, for Gaussian random matrices, which is not general, I mean, this kind of, you don't expect arbitrary matrices to be like that, but this is one nice example. You can actually exactly like, there is an explicit formula for the expected value of the condition number. And you can see that when m is larger than n, this becomes 1. It's perfectly conditioned. So that's basically, that's kind of the intuition for this. So skinny matrix will always be well conditioned. And the longer it is, the more likely it is to be well conditioned. And in that sense, it's clear that only over-parameterized kernels can be well conditioned, because if under-parameterized, it goes the other way around, and the smallest eigenvalue of the kernel is always going to be to 0 just because of rank. So that's basically the intuition. Now, of course, you can say, okay, this is fine, great intuition, but can we prove something about it specifically? And it turns out that for neural networks, we can, at least in some cases. And there are a couple of different ways to control the condition number. And one, we can control the condition number in the following way, which initially looks very special, but actually turns out to be the case for many neural networks. Is that suppose I want to bound lambda min of k of w. Then notice that k of w is the first derivative, essentially. So if I want to bound the change of the k of w, I need to bound the second derivative. So if I have a situation when my lambda min is bounded at w naught, and the Hessian is small in a ball, then I can bound this lambda min in the whole ball. And that's what we call Hessian control. But it's just the idea that you bounding the first derivative by the second derivative, the change of the first derivative by the second derivative. So that's one way, and we will see how it comes in the neural nets. The other way is that you can do, as we discussed this briefly before, you can do some sort of composition control, is that if you know that one function is PL already, and then you're composing it with something which is somehow nice enough, Jacobian is bounded, or inverse Jacobian is bounded, then the resulting thing is also PL. So you can kind of twist the space. So if you know that something is nice, you twist it and it stays nice. And now I'm going to this transition to linearity, and this is the recent finding of Jacob, Gabriel, and Hogler. And they noticed the following. They showed that this neural tangent kernel is actually constant for some infinitely large system. And I'll describe a little in a lot more detail what it means. So what does it mean that it's constant first? And let me first make the following point, is that if you have a function whose tangent kernel is constant in a ball, then the function is linear in that ball. And let me point out that it's not difficult to prove, but it's not completely obvious. Why? Because if just imagine a function with a single output, it's a function from Rn to R. Then saying neural tangent kernel is constant is the same as saying the norm of the gradient is constant. So it's not completely obvious that if the norm of the gradient is, it's not the gradient itself, right? It's only the norm. So in principle, you can imagine that the norm could be constant, but the gradient itself could be non-constant. But yeah, you can prove that if the norm is constant, then the gradient is constant. In any case, either way, the fact is that's why we call it transition to linearity, because really what happens is that these infinitely wide networks become linear. And I think this is just fantastically amazing because I'll discuss this in a minute. There is really no reason for them to be linear. I don't think there is any sort of obvious intuitive way you can say, oh yeah, of course they should be linear. I don't think that's true at all. Okay, so let's discuss now in a little bit more detail what happens here. And if you write the Taylor series, and in some ball of fixed radius, like radius 1, for example, and you write it around the origin, you have this, right? F of W is equal to F of 0 plus GF of 0 plus some Hessian. In this case, it's a tensor because the output doesn't have to be a single number, but you can just write it for a number too. Then what does it mean that this function is linear? And this is a Lagrange remainder term, so psi here is in this ball of psi. So what does it mean that the thing is linear? That means that this has to be small, essentially, right? How do you control this? The Hessian term controls the deviation from linearity. And now you can kind of think about several ways this can happen when you make the network bigger. In the really boring way, you can think it like, okay, if I, instead of taking f of w, maybe as the network becomes wide, I just multiply it by numbers, and these numbers become smaller and smaller, like 0.01, 0.001, and so on. Then obviously, this transitions to linearity. In fact, it transitions to 0, right? Everything becomes 0. This is really boring. Another boring way, you can kind of say, okay, let's rescale the input. I can fix the f of 0, and I just make w bigger. And then trivially, this will rescale linearly, and this will rescale quadratically if I just extend this. And obviously, it will become linear function. So it's kind of like looking at your function through a microscope, right? When you look very, very closely to the origin, if it's a differentiable function, it will look linear. Again, not interesting. But here is an interesting thing. You can rescale the Hessian itself. And if somehow Hessian goes down, then you get the transition to linearity, but not for any of this kind of obvious reasons. And that's actually what happens. And so this is a theorem. You can show that for a neural network, this is jointly with my students, the work for neural network of fairly kind of wide class of network, of which M with linear output layer. Linear output layer is actually very important here. You have the Hessian norm is observed of 1 over square root of M in a ball of radius, let's say 1 or 4. So only the Hessian gets this. So what actually happens is that F stays the same, and the gradient itself in the tangent kernel also, they stay the same. And I think an important thing to notice, which is not really somehow observed in the literature so much, is that this is unrelated to optimization. It's actually a property of the function space itself. As a sort of immediate corollary of this, you can get that wide, well, not immediate corollary, as a consequence, I should say, is that wide networks are PL star in a ball around initialization. And then you can prove that they converge. So how? Because of this Hessian control. The Hessian is small, and then it was already proved in the previous literature that the tangent kernel is non-degenerated the initialization point with high probability. So you just use Hessian control to show that the function represented by neural network itself is PL star. And as a corollary, yeah.
Sorry, Misha. On the notion of Hessian control, we had a question that I missed a little while earlier. Is the notion of Hessian control, I guess the Kartik wants to know if it's something like the opposite of a Lipschitz condition. And I don't know if Kartik wants to elaborate on his question. You should feel free.
Opposite of the Lipschitz condition. I'm not sure I completely understand.
So I might be getting the definition mixed up, but like in a Lipschitz condition, typically you have like you bound the gradient with in terms of how the function value changes. So if you consider Lipschitz of the Hessian, you could say something like the Hessian is bounded by the difference in the gradients. Whereas I think the Hessian control notion went the other way, where he said the gradient is bounded by the Hessian, right? Like the norm of the gradient.
Yeah. So it's kind of a Lipschitz. It's just a Lipschitz conditions essentially for the derivative, right? It's a change of the derivative is bounded by the norm of the Hessian. So first derivative is bounded by the second derivative, right? It's a Lipschitz condition.
Yeah. Awesome. Thanks.
And there was some comment, the model, oh yeah. So there was a comment okay, that was the comment, okay. Yeah. Yeah, and I should point out this relates to quite a bit of recent work on showing that these neural networks converge. In some sense, I think it's kind of maybe a general way to view this convergence result. It's just instantiation of this PL star condition. Okay. And maybe I'll skip this because this is so important, not so important, but there is some sort of, I just would like to point out that it's not necessarily, so there are some explanations which are based on the fact that you can kind of like locally the neural network can be approximated by its linear by its linear part. And I would like to point out this is not what is happening here. It's actually true that the Hessian goes to 0 not because it's just a very small neighborhood. The neighborhood stays the same, and all of these objects stay of the same order as the width goes to infinity. So that there are other regimes in which you get transition to linearity from that, but that's not what is happening, and that's why it's so remarkable. And maybe one more point, at least for people who are somewhat familiar with this. You see, if you look at each parameter stays very close to the origin, and that is true. So if you look at the infinity norm of the distance between the origin and the solution, this actually goes to 0. But the infinity norm doesn't relate to the 2 norm, because you see the Hessian is controlled by the 2 norm, and infinity norm has nothing to do with it. So you cannot get this phenomenon just by looking at the infinity norm itself. Somehow infinity norm going to 0, which is true, doesn't match up with the 2 norm going to 0, and the 2 norm between the solution and the initialization does not actually go to 0. You just get essentially, you get a square, right? In this direction, this is something like 1 over square root of m, but in this direction, it's 1 when it's a high dimensional square, m dimensional square cube. So small change of individual weights does not explain constant anti-gain. Now, let me just give you a simple example to show that this is a non-trivial effect. And the very simple example is the following. Just take a 2-layer neural network with one hidden layer, and you can write it mathematically as simply this sum. So wi's here are some sort of initialization, and vi's I'm just taking them to be fixed random plus or minus 1. Okay, so only one layer, only the first layer is trainable. And sigma here is just some function. It doesn't really matter. You could take it to be a sigmoid. It's some nonlinear function. Oops. I'm sorry. What's going on? Sorry, it seems to be. Okay, good. It's back. Okay, so what do I have? I have first noticed that because it's a sum of m random numbers, at initialization, the output is going to be of order 1, just from the, a sum of m random numbers with mean 0 is going to be of the order of square root of m, and I'm dividing by square root of m, so it's O of 1. Now, it's easy to check that the kernel here is also O of 1. But if you look at the Hessian actually turns out to be a diagonal matrix. And the diagonal matrix with sigma prime prime wjx on the diagonal divided by square root of m. And it's easy to see that the spectral norm of this is 1 over square root of m. So notice that what's important here is that the matrix is diagonal. If the matrix were not diagonal, if it, for example, were a full matrix, a dense matrix with the same entries, right? The Hessian norm would not be 1 over square root of m in general. It would be something like O of 1. So the structure of the Hessian matrix is what makes the norm to be small. It's not the size of the entries, or not the size of the entries alone. It's the fact that in this case, it's diagonal. In general, it is not diagonal, but you can kind of see that there is a more general view of this. And maybe I don't have a lot of time, so I'm not going to spend a lot of time here. But if you actually look at what the Hessian is, and you write the derivative, so Hessian is a second derivative, right, of f with respect to this w's, since these are fixed. You can see that the norm of this Hessian is bounded by the infinity norm of df over d alpha times the 1 norm. It's 2 to 1 because it's the things in general are tensors, but it's essentially just infinity norm times the 1 norm. And the nice thing here is that this 2 to 1 norm is actually of order of 1. And the infinity norm is 1 over square root of m. And that's how it works out. So there is something special about this and about that they interact nicely. Like this doesn't have to be of the square of m, but it happens this way. Now, you notice that this Hessian only has one term. Why? Well, in this case, v is fixed. But in general, if v, you see the last layer is linear in v. So you're not going to have a second derivative in v. If you had second derivative in v, this would not be true. There would be an extra term, which would be of order of 1, something like this here. And this whole thing would break. H would not be of the order of 1 over square root of m. So that's basically how it works. So the Hessian, because of this decomposition, has a small norm, but in contrast, if you look at because it's bounded by the infinity norm of df over d alpha, in contrast, the kernel matrix is essentially the 2 norm of df over d alpha and the 2 norm of O of 1. So what is happening is that there is some mismatch between infinity and 2 norm, which is causing this transition to linearity. So that's why it's a kind of a subtle effect. Now this generalizes to more or less arbitrary architecture as long as they're wide. So instead of having just df over d alpha, you will have several alphas with respect to different layers of the network, and each one of them would be of the same order. Okay, so now let me point out that the natural question here is to ask is that, well, is linearity general? Maybe every big system should be linear, right? Maybe linearity is a general problem, a general property of every wide system. In which case, this would not be so. I mean, it would be remarkable, but maybe a little less interesting in a sense. But turns out not true. So take the same neural network as what we just had, and just put a single nonlinearity at the end of the output. So instead of just taking the output, just put an extra nonlinearity right before the output. Nonlinear last layer. Turns out that this thing would not transition to linearity no matter how wide it is. And why? Well, because as I said, there will be an extra term related to this phi prime prime. and this term will be always of order 1 and will never disappear. So that's basically what is happening. There is some extra term, and this term doesn't depend on the width. On the other hand, if you look at the conditioning of this, you can, oh, I see that there was also a question. I'm sorry, I missed that. The notion of diagonal in expectation. So Harry was asking whether it's diagonal expectation. No, actually, it's actually diagonal for that network. That network is the Hessian for that simple network. The Hessian is always diagonal. If you take, so if you're, I'm sorry. Go back. This one. So for this one, because V is fixed, it's just going to be diagonal. If V is not fixed, it would be like a block diagonal. In general, for multi-layer network, it's not so simple. It's more complicated. So I don't have like it's still a block matrix, but the structure is more complicated. Okay. So yeah, but so you can still prove that this network that we had before is well conditioned. So you would get convergence, but there is no transition to linearity anymore because that last layer thing just kills it. So this is really a mathematical reality. This is not a shortcoming of the analysis that we can prove it somehow correctly, and it's a theorem. So as long as the last layer has non-constant, as long as the last layer is non-linear, you will have a non-constant NTK. And you can kind of do some experiments to verify this numerically as well. This is kind of nice. So this is the change. So what is shown on the x-axis is the network width. The width goes this way. What is shown on the y-axis is the change of the tangent kernel. And the black neural network is the last, it's a nonlinear network, but the last layer is linear. And you see that it becomes wider. The width goes down to 0. The change goes down to 0. When the last layer is nonlinear, for example, hyperbolic tan, it's just kind of constant. It doesn't change. So it's exactly what mathematics would predict here. And the same happens for bottleneck layers. So if you have a single bottleneck layer, all layers need to be wide to have transition to linearity. If you have even a single bottleneck layer, that breaks it. Okay, so let me, I'm running out of time, so let me maybe a couple of summary slides. The first, property for over-parameterized systems, and in particular deep networks. So these networks are non-convex, even locally non-convex, yet they satisfy this PL star condition and behave like linear systems in optimization in kind of a generic way. Wide networks with linear last layers are in fact locally linear. So this is a distinction. In general, over-parameterized systems kind of behave like linear systems, but they're not linear. But if you actually have a wide network with last linear layer, then they are linear. The whole thing is linear. And this is really an amazing thing, and happens as some sort of fairly subtle mismatch between the norm. I don't know. I mean, to me, it's a very, it does look a lot like some sort of central limit theorem, right? When you average some random numbers, you get a Gaussian in there. Not average, but when you divide them by square root of the number, you get a Gaussian. This is kind of like that. When you have a system which is big enough, you somehow get a linear function in there. Not so clear why. Not a general property of large systems, like this last linear layer is necessary, and not explicable by this really simple locality considerations. And finally, it seems to be not necessary for optimization. So somehow you can imagine the world in which this would not be even true, but still it happens. And to me, it's kind of very suggestive because it says, yeah, like maybe like a lot of these neural networks are really linear systems. They're essentially kernel machines, and maybe that's actually pointing us to the fact that in the end, maybe we can explain a lot of things by simply thinking about kernel spaces. So this is the last slide, and so with kind of I'm combining here this kind of idea of generalization and optimization. So we have this kind of two regimes. There is this classical regime when you have a U-shaped generalization curve, and then you have this modern regime when somehow increasing the number of parameters seems to just improve generalization. We call this double descent. The interesting thing here is that if you look at classical models, you have many non-global minima, right? You have local convexity, you have strange behaviors of SGD. In modern models, you have this very different landscapes. They're not locally convex, but in a sense, we have this PL star condition, which I think it's not, of course, not yet at least, a complete explanation for that. But I think it explains a lot about what's going on. And we really now can prove that some fairly big classes of neural networks satisfy it. And somehow there is this mystery, which we still don't understand, is why just doing interpolation, why does it perform so well for statistics? So there is still this mismatch. There is still something we don't understand, like why statistics and optimization fit so nicely. But I think we're now at least have a pretty good idea of what to look for in terms of optimization. And I should stop here, and I'll be happy to take any questions. Thank you.
Thank you so much, Misha. We have one question before I open it up to everyone else, because it was asked earlier, and it is, how do you define the infinity norm when randomness is involved? So I'm not quite sure I understood the question. If Gabin wants to explain, that would be great. Please feel free to unmute.
Yeah, I mean, there was a place where you bounded H with a product of two norms. One was infinite norm and the L1 norm. So I would like to know how we define it, because in some cases we have a topos of matrices. I mean, in case of neural networks model, we have topos of matrices, and then when randomness are involved. So I would like to know how, in this
something
slide,
like this, right? This
yeah.
GF. So in this case, it's just a vector, right? Because M is a fixed vector. And yeah, so when I say 1 over square root of M, it's really 1 over square root of M with high probability. So it is true. It depends on there is some sort of initialization, but it's like saying that it's like the central limit theorem, right? When you have sum of random numbers, say plus or minus, like Bernoulli, right? Plus or minus 1, right? Then you know that this sum divided by square root of M is order of 1.
Okay, I see. So this can be extended in the case of, I mean, when we are in the manifold with a topos of matrices, can we also extend this to that setting?
In this case, there is, I'm not sure I understand the question. In this case, it's simply a vector. So there is no manifold somehow. Could you explain me? I'm not sure I got the question.
Yeah, I understand in this case is a vector. So I'm saying, since we are talking about a neural network and some particular case of neural network, we always have this like a depth n. We have something like n matrices. So those functions are topos of matrices. So I was asking if this property that you present here can be extended in those cases, and if yes, how do we define a norm in that particular case?
No. So in this case, alpha is the what they call like activations or post activations or something. It's just the output. So if you have a say neural network with several layers, you just take df with respect to each one of them separately, and you just take the largest value of each one of them. So that's what happens when you have neural networks with many layers. This is for 2, but you can do it for any number. So yeah, this works for arbitrary. So in general, the claim is that if you have neural network and the narrowest layer is m, then this is bounded by the square root of m. But this is the most narrow layer.
Thank you.
Okay, so if you happen to have more questions, I think you can feel free to unmute yourself as long as we don't end up with too many people talking.
I have a question. I was quite surprised to hear that if you have a non-linear output layer, you never have a linear regime. So, I mean, would this include, say, if you had a softmax output layer?
Yeah, it's always true.
Because I know most calculations involving NTK are usually written for a linear output layer, but I always assume it's for convenience. And I remember there's one paper that I think tests the NTK prediction with softmax output, and they find good agreement. It's a paper called "Wide Neural Networks of Any Depth Evolve as Linear Models Under Gradient Descent" by people from Google. I don't know if you're aware of this paper. Lee, Xiao, Schoenholz, Bari, Soldigstein, and Pennington.
Yeah, I don't know that one, but yeah, it's they're never going to be linear unless the last layer is actually linear. The thing is, okay, I have to be a little bit more specific. So there could be ways where maybe like if you have something very special, maybe you can be linear like when you optimize somehow, but I don't think even that is possible. Because your optimization pass, right, is a subset of the whole space. But yeah, you can actually see the picture here. So if you look at this picture, so the black one is the linear activation, the linear last layer, and non-linear the layers before, and the blue and the red are different non-linear layers, and you can see that they're just constant. The change of the tangent kernel is constant.
And this is trained with gradient descent, SGD or
SGD or gradient descent. I don't remember which.
Okay, well, very surprising.
Yeah.
Thank you.
Yeah, because there is a term which doesn't disappear, so it's not. Yeah.
So while people think of other questions, I have a quick one. How dependent is this analysis on having the square loss?
Okay, there are several things. Yeah, transition to linearity is completely model independent, right? That's just a property of the model itself. A model with certain property will be close to linear in a ball of a certain radius. For the
But the optimization is
optimization is, of course, right. So there are a couple of points here. It's not really dependent strongly in the following sense. You can, for example, if instead of the square loss, you take the forced power, you can get very similar thing, except it's not as nice because for square loss, you get this lambda mean. For these things, you get some function of lambda min. It just gets more complicated. So, but it's not really dependent so strongly. Now, what people do in practice, they use something called cross entropy. And cross entropy is very strange because the minimum of cross entropy is actually at infinity. It just, you need to go to infinity. The norm of the weight has to be infinity to minimize a cross entropy. And that is very problematic from this point of view, because this transition to linearity always happens in a ball. And the radius of the ball, of course, increases, but it's a function of the width of the network. But if you want to drive your cross entropy to zero, you always have to go to infinity. So you will always leave this ball for any fixed size. So that, I think, if you run it to infinity, you will never see transition to linearity. In practice, people don't run it to infinity. They do some sort of early stopping. So then it becomes a very subtle question, like how early is early and so on. But in principle, if you really run it to infinity, you will always break this.
Great, thanks.
And also, I should say that proving stuff is harder, right? Because you're going to infinity. I think I've seen recently there was some work where they proved that you could converge, but it's harder because you have to somehow control it along the whole path to infinity, not in a ball.
I have actually questions. So concerning actually passing with the widths to infinity. So it seems to me that this is rather essential, but I could imagine that, I mean, often you actually take more and more layers rather than taking the widths of the layers to infinity. And so the way I understood the original paper on this neural tangent kernel is that they actually don't look at this on the parameter space, but look at this on the resulting networks. And then if they actually take the widths to infinity, I mean, they get a convergence to a constant kernel, which means that like if you consider like this, the space of networks, you live in a linear space, and that this is the reason why you actually have this nice behavior. But now if you don't pass to infinity, then I mean, you may get quite different behavior. So we did an analysis like for linear networks, but where actually we also had the case of an autoencoder in mind, where it would actually not be very useful to take the layers to infinity. So can you comment on this?
Yeah, so it seems that taking layers, so right, there are two limits, right, you can take potentially. One is taking the width to infinity, which is what I discussed here. Another is taking depth to infinity with maybe an infinite network or maybe with a finite network. So we actually did some work with Adit Radhakrishnan and Caroline Euler. We did some work on trying to understand the depth. And it looks like that what happened there, at least in some cases we can prove, but what we observed actually empirically, in a sense more interesting, is that it seems that it almost does something like one nearest neighbor when you go to this limit. It listed. Mathematically, we could only prove it for special cases, but empirically it seems pretty consistent. And so basically what happens is that it kind of becomes this, for auto, and I should point out this is for autoencoders also, it becomes this kind of piecewise constant function in the limit. How does it relate to this going to infinity in width? It's unclear, I don't know.
Yeah, okay, but my question is also like if you have like some realistic network, I mean, what does it mean that you're close to infinity also? Like, I mean, apparently you get all this behavior in practice, and your analysis to indicate that there is a good reason for this. But I mean, can you quantify this also, like how large M needs to be?
Well, so people have done this. There are several papers recently when people have used this kind of infinite networks for predictions, and they seem to work quite well. Because in some cases you can write it down explicitly, the infinite kernel. But I mean, you're asking how wide it needs to be to get this. Is that the question?
Yeah, more or less.
Yeah. It's unclear. You know, we've done some experiments, and experimentally it seems that wider networks are almost always better, at least a little better, not necessarily maybe greatly better. But you can, in some cases, you can write down explicitly the infinite model, and it seems to perform quite well. So there is some sort of fairly slow improvement. So I don't know. I have difficulty quantifying it. So maybe the honest answer is that I don't know.
Okay. And another technical question. So your PL star condition, I mean, do you define it for the whole space or for a subdomain? Because you made this picture where you had these several domains where it holds.
Yeah, so it's something like this, if you can still see my screen. You basically want PL star to hold in some sort of ball. And then if you somewhere initialize somewhere inside this ball, then you're guaranteed convergence. So you can define it pointwise, of course, but it's not useful, right? It's only useful when it's in the ball. It's some sort of uniform.
Okay, but you don't require it for the whole space, like for any input.
No, it can never be true for, at least for neural networks, it will not be true for.
Yeah, and just another comment. So we did this analysis for linear networks, and then we stumbled across a situation where we get actually a zero Hessian in like critical points with zero Hessian, and these created problems. So I guess your condition will also not hold in such cases. Yeah,
and we know they exist for neural networks. You can find them.
Okay. Okay, so your analysis works if you're in a region where no such points exist.
More than that, we can prove that if you initialize at random, you're likely to be inside such a region.
Okay. Okay, yeah, thanks.
So generically, it's true, but if you look for points with Hessian 0, you will find them.
Thanks.
Hi, I have one more question about the basically if we impose penalties on the, so you didn't impose any penalties. I was just looking at the L2 loss. What happens if you impose penalties? Will you have to change this PL star to some other condition? Because penalties can, I think, kind of improve the landscape a little bit, right? And the local minimum may have some better properties than without any penalties. So will they change the PL star property to something else, or maybe like the convergence rates will improve just because of the penalties? Do you think that's possible?
So when you say penalty, what do you mean by that?
So like you have the L2 loss of fitting your parameterized family to your data, and then adding another term which is imposing some penalties on the weight, like for example, like the L2 norm of the penalties or some other functional imposed on the penalties.
So penalties are a little problematic because what happens is that once you have a penalty, you cannot generally have interpolation. So you can maybe be close to interpolation, but right, because once you put some sort of regularization, you cannot fit the data exactly. It will prevent you from doing
Not
that.
exactly, but approximation is possible depending on the penalty.
So if the penalty is small, what you can prove that initially it just behaves like as if it's PL, but then of course once you get closer to where penalty makes a big difference, then of course it breaks, and you don't, like for example, stochastic gradient descent will not, with a fixed step size, will not converge at all if you have a penalty.
I see.
Right, it will just oscillate once you close enough. If you have pure PL, then stochastic PL star, I should say, then stochastic gradient descent will converge. So there is a regime where penalty doesn't make a big difference, but once you get kind of closer to hitting your constraint, then you essentially transition back to the classical regime. You get non-convexity, you get everything, like this kind of local minima and so on. So in a sense, that's a nice thing about interpolation. It kind of allows you to completely be in this very pure setting.
I see. Yeah. The penalties are kind of interesting because I think it's possible sometimes actually even like any local minima can have some really nice properties with any like a local minima until some good penalties, like non-convex penalties. They can approximate well and also have like sparsity properties and things like that. So it would be interesting actually if kind of there is some kind of connect, like another property similar to PL star checkable that would guarantee kind of good convergence with this kind of penalties.
Yeah, I agree. I think it would be very interesting to see how it and in practice people do use penalties frequently.
Mm-hmm. Yeah.
So it's
Right. Thank you.
Okay, so I guess I will give it 2 seconds to see if there are any more questions. If not, I think we can thank Misha one more time. This was a very stimulating talk, and we'll see you all next week. Thank you.
Thank you very much.